Warm welcome, everybody. And thank you so much for joining today's session. My name is Károly Sipka. I'm one of the founders and CEO of iPercept, and also one of the inventors behind the concept of the motion analysis, which is the outcome of long years of research from the Royal Institute of Technology in Stockholm. And today, we are going to talk about the monitoring of complex CNC machines. Specifically, why the traditional approach is no longer enough and what has changed. Before we begin, a few quick notes. The webinar will be recorded. We will send a follow-up email with the content of this webinar. During the session, please do write your questions as they come up. They will be answered at the end of the session, so we can keep a good flow throughout the whole material. In the next 30 minutes, I will walk you through why there is a gap in how CNC machines are monitored today, what has changed in sensor technology, and what this means for your Monday morning catch-up meetings. So let's get started. And what we will cover today is that what is the problem with the business as usual? Why vibration monitoring falls short for monitoring complex industrial machines? And what is this paradigm shift from measuring vibration to measuring motion? Then we will dive a little bit deeper to the motion pattern method and turn into real-world impact cases, while in the end we will summarize the key takeaways and look into the next steps and have some time for the question and answer. But let me start with a simple question. Think about the most important CNC machine in your shop floor right now. On a scale of 1 till 2, how confident are you that you know the real health of its x-axis? Not what the operator thinks, not what the last service report said, the actual current condition of the ball screw, the guides, and all the bearings in that axis. In my experience, most answers fall somewhere between 3 and 5. And this is not because anybody is doing a bad job. It's because the tools available today simply don't give you that level of insight for complex CNC machines. That's the gap we are going to explore today. And maybe most importantly, how to close it. So if we are looking at the CNC machines and how they are monitored today, the reality breaks down roughly like this. About 60% of maintenance events are reactive. Something breaks, quality drifts, or the operator hears something unusual. Then you scramble to fix it, and usually this happens in the worst possible time. About 30% of the maintenance budget today goes to calendar-based replacement. You change all ball screws or bearings every X thousands of hours, whether they need it or they don't. Sometimes you are replacing perfectly healthy components, and sometimes you are too late. And the actual condition-based monitoring on CNC machines, now that represents less than 10%. Not because people don't want it, but because the traditional condition monitoring toolkit based on vibration analysis was designed for a completely different type of equipment. Fans, pumps, compressors, single bearings. Simple rotating machines or components. A 5-axis milling machine is a fundamentally different animal. And that's where the story gets really interesting. Most manufacturers spend more on emergency repairs for a single unplanned CNC breakdown than they would on an entire year of continuous monitoring. The cost of not knowing is invisible until it hits the production schedule. At the same time, many companies spend excessive time on weekly manual inspections trying to catch issues early, reducing both reactive downtime and planned inspection time is the real opportunity. So let me give you some context on how on why we are here today and where we are today. The condition monitoring as a discipline goes back to the 40s, when the first piezo accelerometers made it possible to measure vibrations. In the 1970s, fast Fourier transforms, FFTs, unlocked frequency domain analysis. That was a real breakthrough. Suddenly, you could identify specific bearing defects, frequencies, imbalance patterns, and so on. Over the following decades, the technology went wireless, went digital. AI was mixed with it and adapted widely for rotating equipment. That's the key point. For over 80 years, the industry optimized vibration analysis for one type of machine, things that spin, fans, pumps, compressors. But CNC machines with multiple axes and subsystems, they need a fundamentally different approach. And the technology to make that possible only became available in the last decade with the revolution of microelectromechanical systems sensor technology. Here is a scalability problem in one visual. If you wanted to properly instrument a 5-axis milling machine with traditional vibration sensors, researchers have shown you would need sensors on every bearing, every motor, guideway, ball screw. That can easily mean 30 or more sensors on a single machine. The cost and the complexity of this is just enormous. And if you replace one sensor, you lose its entire measurement history. Now compare that to a motion-based approach where you only need one device which moves together with the whole machine, meaning one or two devices for a full machine with decoupled kinematic chains. It can provide no connection to the machine controller to be standalone, no cybersecurity risk, no IT infrastructure changes. Fully retrofittable to any CNC machine, regardless of the brand, if it's old or new. The analogy I sometimes use is trying to monitor a CNC machine with only vibration sensors is like trying to diagnose a patient by only checking their heart rate. You will catch some things, but you will miss the bigger picture. Motion analysis unlocks an analogy to a full X-ray scanning of the body, getting an understanding of every single part of the body. Before we move to the solution, let's make sure we understand the 3 core limitations of the traditional approach. These are not implementation problems, much more like architectural ones. So first, the baseline trap. Traditional systems detect deviation from a learned baseline. Replace a sensor, the baseline resets. Replace a component, the old threshold may no longer be available or applicable. You are always chasing a moving target. Second, the threshold dilemma. Even with enough sensors, defining meaningful thresholds is extremely difficult. Not every degradation requires action, but which one do? Without component-level context, alarms become noise, and noise leads to alarm fatigue, which is arguably worse than no monitoring at all. And third, the physics limitation. Piezoelectric sensors measure high-frequency vibrations only. They cannot capture gravitational force or low-frequency motion, and that's precisely where many CNC failure modes first become visible with extremely high sensitivity in the way how the machines move and not just the way how it vibrates. Now let's talk about what has changed. Over the last decade, MEMS sensor technology, microelectromechanical systems, has undergone exponential improvement. Cost has dropped roughly 100 times, size has shrunk by an order of magnitude, sensitivity has increased by an order of magnitude, and the noise floor has dropped dramatically. What was unimaginable 10 years ago is reality today. Aerospace-grade MEMS accelerometers now match and in many areas actually surpass the traditional piezoelectric sensors at the friction of the size and the cost. And critically, unlike piezoelectric sensors, MEMS-based inertia measurement units can measure gravitational force. That gives us an absolute reference point. It means we can capture both high frequency vibration and the low frequency motion at the same time. That's the technological breakthrough that makes everything we are about to discuss possible. And I should also add that these are not the sensors what you will find in a smartphone. These are purpose-built aerospace-grade sensors designed for precision industrial measurements. So, what does this look like in practice to unlock the motion pattern detection? What we need for this is not a single sensor, it's a complete measurement system. We need a combination of over 20 individual sensors with 4 fundamentally different specifications. Some are optimized for ultra-high sensitivity, detecting micrometer level degradations in motion patterns. Others are designed for ultra-low noise, filtering out environmental interferences. They cover multiple overlapping frequency bands, so nothing is missed. The key insight is that the strength of each sensor covers the weaknesses of the other. That's why a single device can replace an entire network of traditional vibration sensors. It captures motion coupled together with vibration, high and low frequency with a gravitational reference, the full spectrum from one single mounting position. To summarize the practical implications, one device per kinematic chain, capturing the full motion signature, moving together with the machine, zero connection to the machine controller, no cybersecurity risks and no IT projects, retrofittable to any CNC machine, let it be old or new, and the device automatically detects when a test cycle is running and makes it possible to only rely on the data from these test cycles, so the system stays blind for during production data. The barrier to getting started is much lower than most people would even assume. So here is how the test cycle works. Instead of monitoring continuously, which creates data overload and cybersecurity concerns, we can use a predefined machine movement sequence, a short G-code program that takes about 5 minutes to run, typically once per week. The test cycle includes 4 types of motion. The spindle test runs the spindle at different speeds across its working range. Then the circular test engages 2 linear feed drives simultaneously in both clockwise and counterclockwise directions. And then the linear test runs all linear axes one by one from the end to the end of their maximum stroke. And if the machine has rotary axes, the rotary test runs those rotary axes through their full swivel range. Together, these 4 tests exercise every subsystem and every critical component in the machine. And because the machine is inherently repeatable, we are talking about millisecond level timing accuracy, what we can really rely on. Any deviation from the expected pattern tells us something specific, what is degraded in the machine and where. The workflow is straightforward. Install the device on any metalworking machine with just a 24-volt power supply, run a weekly test cycle that takes about 5 minutes, can also be implemented occasionally or every day. The algorithms automatically analyze the data and turn it into alerts, trends, and recommendations on a component level. So insights become really specific, such as you have a critical degradation in the nut of the ball screw of the axis, or you have a degradation of the drive side bearing of a Y linear axis, but it's stable, just keep up the monitoring. And this allows to plan and prioritize maintenance based on the machine's actual state rather than just assumptions and gut feelings. Component level insights within a week for any machine, and this is the starting point. Now, let me explain and unpack a little bit the intellectual core of this approach, the motion pattern method. The traditional approach is relative. Compare today's signal to yesterday's signal. The problem, if the machine was already degraded, when you started monitoring, you will never know it. The motion pattern method is absolute. We compare the real motion pattern from the test cycle against a physics-based digital twin, a virtual model of how the machine should behave when it's healthy. This means that we can detect degradations from the very first measurements. No learning period is needed, no baseline is needed, and no need to wait for that something fails first. The digital twin uses physics-based simulations to predict how specific types of degradations affect the motion pattern. Now, imagine that part of the test cycle when we are moving together with our high sensitivity sensors with a linear axis back and forth, back and forth. Now, imagine that there is a degradation in one of the components of that linear axis. That is going to have an implication on the motion pattern of the machine. Given the right sensitivity, we can detect it. Given the right pre-trained models, we can translate it to the root cause, and even better, the pattern changes as the issue escalates. And so we are able to connect it also with the severity of the problem. So bearing damage creates one type of pattern. Ball screw nut damage creates another. Ball screw shaft or rail detection another. And so the system is able to identify and distinguish between them. And what is also very important, to find when they are not present, when the axis is actually healthy. That is the absolute component level identification. Let me show you two quick examples of what does it look like in real data. On the first slide, we will see two machines, same machine brand, same axis type. Machine one shows a clear motion-dependent defect, spikes in the acceleration profile of the very beautiful moment when a linear axis is changing direction from positive till negative. These reversal spikes contain an enormous level of the mechanical complexity of the machine. So the algorithm is analyzing this moment very, very carefully. Here we see on the comparison that even with our bare eyes, we can see a motion, a pattern appearing. With the right algorithm, we can connect this with its root cause, that this is related to the ball screw nut. And on this slide, a position-dependent defect. Looking at the time domain signals, where it's an abnormal burst at a specific position along the axis travel. This 2D spectra confirms that a localized degradation on the rail was identified, and when the maintenance team opened the machine, then they really found the visible damage and documented it with images. That's the kind of specificity we are talking about. Not that something is wrong with the x-axis, which is extremely difficult to act upon, but there is a surface defect on the guideway at this specific location. On this slide, we can see the PF curve, the potential to functional failure curve. It's a core concept in reliability engineering, what we will not deep dive into now. But the key question is that how early can we detect that the component has started to degrade? The earlier you catch it, the more time you have to plan. You have to plan or prioritize your response for this. And this is the window which is called the PF interval. Now, if we look into the bearing degradations, this PF curve and the diagnostics of bearings have been extremely well researched. By being able to distinguish between different patterns of bearing degradations and saying that what is the degradation stage of a bearing. What we have done, we expanded this concept for every single component of any CNC machine out there, where each degradation stage tells us that not just that what is happening, but also that how urgently one has to act on it. Stable means that the subsystem is healthy, continue monitoring. Observable means early signs of wear are detected, start planning maintenance. And accelerated means degradation is progressing rapidly, from which it's possible to extrapolate. And any additional stress or collisions can actually mean a really high risk for a catastrophic failure. So start to schedule the repair. And critical means you are close to the failure and need to act immediately. Based on the sensitivity of the production, this not just means to avoid unexpected downtime, but it also means saving product quality. A replaced ball screw does not always solve the whole problem. When one component degrades, it can propagate the damage to the neighboring components in the whole kinematic chain, couplings, bearings, guideways. Without component level monitoring, you might replace the obvious part and then wonder why the machine still doesn't perform and fail again within 1-2 months. Motion-based analysis reveals the full picture. Now let's look at this. What does it mean in practice with some real-world cases? In the first case, an aerospace manufacturer with a 5-axis milling machine. Between 2 routine cycles, the test detected a sudden localized defect on the shaft of the ball screw. The pattern was actually consistent with a severe collision event. Importantly, the system confirmed that the damage was only isolated to the single subsystem and the shaft of the ball screw. No other components were affected. Without this level of monitoring, the standard response when a critical aerospace machine shows unusual behavior is oftentimes a full machine renovation, plus weeks of downtime, plus potential huge quality losses. Instead, a targeted repair was performed on the confirmed defect only, restore the health of the machine with an estimated saving of over $250,000. That's the power of knowing exactly what is wrong and, equally important, what is not wrong. Then on the next case, an early detection of a spindle degradation ensured timely response from the OEM, where spindle could be ordered just in time, which was not on store, and the proactive action prevented a potential 2 to 3 weeks of unplanned downtime, with estimated savings of the 70 to 90,000 euros. Then the third case is a very different kind of value. A general manufacturer used motion-based monitoring to assess the health of their entire machine fleet. The data showed that one machine could be safely decommissioned with 0 productivity impact. The remaining machines had enough capacity. Other machines received targeted maintenance that extended their useful lifetime by more than 3 years. What I find most interesting in this case is that it turned a capacity question, which in many cases is rather a political discussion in manufacturing companies, into a fact-based decision. The data spoke for itself. So let me leave you with 5 things to remember from today. 1. Vibration monitoring was designed for simple rotating equipment. CNC machines need motion monitoring to capture the full picture. 2. MEMS sensors technology has improved exponentially. 100 times cheaper, dramatically smaller, higher sensitivity, lower noise. What was impossible a decade ago is now production ready. 3. The motion pattern method uses physics-based digital twin for absolute degradation detection. No baseline needed, no lengthy learning periods, component level specificity from day one. 4. 1 or 2 devices per machine, each containing over 20 specialized sensors. No controller integration, fully retrofittable. The barrier to entry is much lower than people assume. Then 5, motion-based monitoring doesn't just detect problems, it tells you exactly which component and how severe and how urgently you need to act. So here is my challenge to all of you this week. For your most critical CNC machine, could you describe the health of each axis and the spindle right now? If the honest answer is not really, you have identified exactly where the gap is. And now you know what is possible. So if you found today's session useful, here is what's coming next. Session 2 is going much deeper into the motion pattern method, the technical methodology we introduced today. Session 3 is going to cover the subsystem and failure modes related to any linear axis, rotary axis, spindles, and how they can actually fail. And session 4 is a practical guide to getting started with digital monitoring without disrupting your operations. And session 5 will cover operational monitoring with process load intensity and utilization monitoring without any hardware updates. So thank you so much for your time and attention today. I hope this gave you a new perspective on what's possible for CNC machine monitoring. Have a great day and week ahead. Goodbye.